at Sacramento at your listening station, you hear 010 and you say, that can't be right. What's the simplest thing to do to try and find out what the weather really is? Because you know that an error has occurred. We've talked about the most compact way to transmit this information. There are 4 possible patterns. You can have 2 zeros, you could have 0, 1, 1, 0 and 1, 1. However, we've got to be careful here, because what we've done, and referring back to what I've said previously about compression methods, what I've done here is devised a code which has no redundancy at all. We've talked about how to squeeze redundancy out of text files and pictures, which is what compression is. It's getting rid of unnecessary information. There's nothing unnecessary here. Every one of those bits is vital, and you better hope they don't get lost or distorted on the way. Unfortunately, they might get lost or distorted on the way. So the next thing we have to say is these codes are beautiful, but they rely on you having clean, noiseless communication across your telephone wire. What would go wrong if that wasn't the case? Just occasionally, one of these 0 bits, that's signified by a short boop for a dot, might get turned into a 1, because part way to Sacramento, suddenly an electrical storm occurred and just hit the telegraph wire. So what was received at Sacramento was not do do, it was do da, like that, a longer second bit, and the people said, oh, that's 0, 1. It's sunny in San Francisco. No, it isn't, it's foggy. So you can see very quickly there is no possibility for recovering from error in these. If you get an error, people will receive apparently a good pattern, but it will be for the wrong weather condition. How could you add something extra to these to give them a bit of protection against noisy telephone lines? The simplest way, one of the simplest, has been used in telecommunications and indeed within computers for years and years now. You put in a parity check bit. So here's a code with a check bit, and all I'm going to do here, I will take every 2-bit code and turn it into a 3-bit code. But the rule will be that in the overall 3-bit code, I must have an even number of 1 bits. So this is called an even parity system. So here we go. 0, 0. There are no 1s in that, so therefore at the right hand end here, I'm going to add in the parity check bit, and because we're on even parity, it's a 0. Viewers of Numberphile will have to forgive me. I think there is a video on there questioning whether 0 is an even number. I'm sorry, I'm just a computer scientist.
People have a delayed reaction. People are not sure whether 0 is an even number.
That's even as far as I'm concerned. Okay, how about this one? 0, 1. Well, overall, it's got to be even parity, which means an even number of 1s. So my bit I add at the right hand end is a 1. Equally here for cloudy, 1 and 0. There it is, 2 of them, 101. Rainy, that's easy. There's an even number of 1s already. So I put a 0 at the end. Now those codes with the check bit, they help a lot in helping to detect whether an error has occurred. Just suppose that when this 000 was sent, it got distorted. Again, an electrical disturbance just happened to chew up one of the 0 bits, lengthen it and make it look like 010. If any of these got distorted, a 0 turned to a 1 or a 1 turned to a 0, it looks like a valid different weather state. Here it doesn't, because look at the valid codes. 3 zeros, 011, 101, 110. I sent this and it arrived at the other end as 010. Is this a code that's in this set? No, it isn't. If you try with these, just changing any one of the bits and flipping it, either a 1 to a 0 or a 0 to a 1, you end up with something that isn't in this list of good, valid codes. You could say, well, there's bad codes. There's things that don't correspond to any of these. And of course, with 3 bits, 2 to the power 3 is 8, so there's 8 possible combinations. What we've done here is split them up into 4 good codes that are meaningful and 4 bad ones, but the bad ones give you a protection against errors in transmission. At your listening station, you hear 010 and you say, that can't be right. What's the simplest thing to do to try and find out what the weather really is? Because you know that an error has occurred. Well, the simplest thing is to send back to San Francisco a simple 1-bit message, either a 0 or a 1. You either say acknowledge, in other words, I got it, it's a good code, or not acknowledge. Here I would send back a not acknowledge, often called a NAC for not acknowledged. I send back a 1-bit which says not acknowledged, got garbage, and the sending end would say, okay, let's keep it simple, just send it again. 0, 0, 0. Next time you hope it's going to get through without distortion. So this is the basis of this system, in that it can detect that a single error has occurred. The only trouble is that it can't tell you where the error occurred. Just consider the following. I have got 010 here by changing the middle 0 into a 1. But it could have happened that it came from this one via distortion. It could have been that the bit that got distorted was not that one or that one, but that one. That trailing 1 bit might have got turned back into a 0. There's an error, but I don't know whether it came from this one or from this one. So this kind of code then can detect one error, but it can't correct it. It can't tell you where it occurred. Suppose I had an even noisier line, and that in one of these 3-bit codes, you hope most of them are going to go through cleanly. You hope that the ones that aren't clean will have at most 1 error in them. What happens if I send 101 and there are 2 errors in it, not just 1? The errors just so happen that it turns a long blip into a short one, there and there. That would then give you 0, 0, 0. 2 errors. Oh, calamity again. This is received at the receiving station. They say, hey, fantastic, 0, 0, 0. It's foggy in San Francisco. No, it isn't. It's cloudy, but it got 2 errors, so it looks like it was foggy. So the point here is it's resilient against 1 error. It can detect it, it can't correct it, but against 2 errors, there isn't resilience. It distorts it into a good-looking code again. So for this reason, this system is called a distance 2 code, because what it's saying is if you flip 2 bits, it changes into another good code. If you flip 1 bit, it's discernibly garbage and you can say an error's occurred. It's 80 megabytes. And let me say again, 80 megabytes, not 80 gigabytes. And it's in this huge package.
Any combination of art and science that goes into making a game is an extraordinary thing.